In this video, we will be building a macro that will allow us to track the allele frequencies of the A1 and A2 alleles across multiple generations or multiple time steps. We've set up time steps down column K that begin with the number 0 and end with the number 20. And for each and every time step, we'll be tracking the number of parents and the number of offspring that they produce, and we'll be tracking the frequency of the A1 and A2 allele for the parental population. Now to begin, we enter the number of parents in cell B5 and the number of offspring in cell C5, and we also will hard code those into cells L9 and M9. Now you might remember that when we begin our simulation, we used a random number and we referenced the frequency of the A1 allele that's stored in cell D5. And we used this number to generate genotypes for our parents. But you might also remember that because there's some randomness involved in this, that the actual realized genotype numbers and the realized allele frequency for the parents may not perfectly match what's in cell D5. Now our macro is going to include a few steps. First of all, we establish our initial inputs. We've already covered that. The second thing we need to do before our macro is we need to establish the offspring population size down column M. And these are the cells that are shaded green. And a key assumption for this exercise is that the parents have offspring, and then in the next generation all of the parents die, and the offspring then become the parental population. So we'll enter equals M9 and copy that through, and now we have both the parent and the offspring populations for each and every time step. Now our macro is going to do a few things. The first thing we're going to do is to turn on Excel's manual calculation option. And this allows us to control when the cells are actually computed or calculated. Then the second thing is we're going to find the frequency of the A1 allele for the parental population and store it in the correct place down column N. That's our key thing for this macro, is we want to be tracking the parental A1. The next steps of the macro, though, will get us all set up for creating the parental population in the next time step. So to do that, we're going to take all of the offspring in column H and paste them directly over the values in column C. And then we're going to then update our allele frequencies that are calculated for now this new parental population. But to do that, we need to adjust the counts in column B so that they reflect the new population size. And to do that, we're going to come back to column N and find the appropriate time step, and then we'll find the parent and offspring in the next time step and paste them into cells B5 and C5. That's a mouthful, but I think you'll see how this works as we walk through it. We then press F9. That generates these count numbers, which allows us to compute the correct A1 frequency, and it also generates new offspring for those parents. At that point, we are done with our macro, and we can run it for multiple different time steps. Okay, let's give this a try. First we'll go to the View tab, and then we'll choose Macros, Record Macro. And you can call it whatever you'd like to. I'm going to call mine Generation. You can tell Excel is recording because it will display a square at the bottom left portion of your screen. So the first thing we're going to do is to turn on Excel's manual calculation, and we do that by going to Formulas, Calculation Options, and then changing it to Manual. This means that in order for the spreadsheet to calculate, we must press F9. The next thing is to copy the frequency of the parents. That's stored in cell L4, so we'll copy that. And then we'll paste that value in to the corresponding time step. And to do that, we'll select cell N8 and we'll find the next blank cell down column N. So we'll choose the binoculars and we'll choose Find, and a dialog box will appear. If yours is collapsed like this, you can expand it by pressing the Options button. And we're going to find the next blank cell, and we want to make sure that we search down columns. And when we press Find Next, we should see that this box drops down one row. And it does. We press Close, and now we can paste that allele frequency in. So all we have done to this point is to properly copy and store the frequency of the A1 allele for the parents in time step 0. So now we're on number 3 here, and we're going to set up our conditions for the next generation. So those parents can reproduce, and then in the next generation, their offspring will become the parents. So we need to copy the values down column H, and then we'll select cell C9 and we'll paste the values in. So we're no longer simulating, we're actually pasting the values in. We're getting ready to calculate the new frequency of A1, but to do that we need to adjust this count column. And to do that we need to know how many parents and offspring will be in the next generation. So we'll select cell N8 once again, and this time we'll find the next blank cell. And again we'll search down the columns. And you can see it's dropped down now to time step number 1. And here we want to move our cursor and highlight the 2 cells that are to the left. And before you do that, you need to turn on Excel's relative reference function. And you find that in the View tab under Macros, and then choose Use Relative References. So we'll use our arrow key and we'll arrow over twice, and now we'll press the Shift key down and we'll arrow back over one more. So we're copying now the parent and offspring population sizes in the next generation. Now at this point the relative reference is done, so we'll go back up and we'll click off the Use Relative References, and we'll copy whatever we've selected here, and then we'll select cell B5 and we'll paste the values in. So you can see that these numbers were correctly placed in cells B5 and C5. The next step then is to press F9. And this does several things. First, it tells Excel to calculate the results. So now you can see that the number 1 is entered for the first 16 individuals down column B. That in turn allows a correct calculation for the frequency of the A1 allele in the next time step, which we'll record the next time we run the macro. It also generates new offspring genotypes through that random process, and it begins a graphic that will track our frequencies through time. So the last step here is to turn off the manual calculation. And again we go to the Formulas tab, we choose Calculation Options, and we switch it back to automatic. And at this point our macro is done. We can stop the recording, and if you choose the View tab and open up the Macros box and choose View Macros, you should be able to see your macro stored there. Now to run this macro, you can simply insert some kind of object, a picture or a figure or a text box, and then assign the macro to that particular image. So I'm going to enter a text box, and it's going to be labeled Run. And while the text box drawing tools are up, I'll choose Format, and we'll highlight and format our text box a bit. And then if we right-click on it, we can assign our macro to this particular text box. So if we choose Assign Macro, and then select on the macro itself, now when we press this button, it will execute the code that we've just written. Let's try it. So in running this macro, what we should see happen is the parental population's A1 frequency should drop down and be stored in the next open cell in column N. And we should see that the next parental population size and offspring population size get moved over into cell B5 and C5, which prepares us for yet another generation. Let's try it. If we keep clicking, you can see that our frequency of the A1 allele is fluctuating over time, and this almost certainly is due to the very small population size we have here. Let's keep running it. We're at now 0.92, 0.97, 0.92, 0.93, 0.96, 0.93, and finally we hit the number 1, and at that point the A1 allele is fixed. And what does that mean for the A2 allele? Right, it means that the A2 allele is extinct. So we've just witnessed a loss of genetic diversity through this process of random genetic drift. We can quickly display the A2 frequencies by just entering 1 minus the frequency of A1 and copy this through. And that will depict both the A1 and A2 frequencies over time. So here again you see the extinction of the allele A2 and the fixation of allele A1. Now this result represents one trajectory, one possible outcome for our initial conditions. What if we wanted to repeat this experiment? Well, to do so, we'd want to reset the genotypes for the parents down column C, and we'd want to erase our results so that we could begin with a clean slate. And to make it so that we can easily do this, you got it, we'll write another macro. So let's go to View, Macros, record a macro. Let's call it Reset 1. And again, we're recording. So if we're going to reset the entire exercise, the first thing we'll do is we'll delete our initial population sizes, and we'll delete all of our results. And then the last thing we need to do is to reset our initial genotypes so that they're drawn at random as we had in the past. So we'll copy cell B6, and this time we'll select cell C9 and we'll paste the formula in, and then we'll copy that all the way down. So now we're starting with a brand new clean slate. We press stop, and now we can add another text box and call it Reset. Format that if you'd like to. And then we'll tag that to our macro that just resets our results. So we'll assign the macro reset1. So now when you run a macro and you're going to run an experiment, again, first you'll need to hard code your initial parents and offspring, and then you'll press run. And this time you can see that our allele for A1 is fluctuating quite a bit, and actually it does go to fixation by the year 19. And again, if we wanted to reset this, we would press reset, and now we're ready for another simulation. So we need to again establish our starting populations, and off we go. Now, I'll bet you can guess that we're going to be using this macro and exploring this a lot more in our sandbox homework problems, and you'd be right. We're going to be able to look at what happens under different population sizes, what happens when we keep the population low for a long time versus keep the population low for a short time. And we'll be exploring just how general changes in the population overall will affect these allelic diversities.
Thank you, Terry. I hope that spreadsheet exercise was really helpful in terms of understanding how the mechanism of genetic drift operates on populations and how it affects populations of different sizes. So we've covered a fair amount in this module, and let me just take a moment to recap some of the highlights, some of the key points to genetic drift. So we know that genetic drift is a random process, and we could define it technically as the chance fluctuation in allele frequencies as a result of random sampling among gametes. Again, a bit of a mouthful, but I think you probably understand what this means at this point. And we could probably more simply state it as the change in allele frequencies that occurs by chance alone, without any sort of influence from a directional force like we might see from natural selection, for example. But genetic drift is a force. It is an evolutionary force, and it can lead to substantial changes in allele frequencies in populations. What are those effects? How does it affect those populations? Certainly in some cases, especially small populations, it can lead to some alleles being lost in that population. It can also lead to some alleles becoming fixed, so every individual carries the same allele. Sort of the same thing that happens when you have one allele being lost from that population. So loss of alleles, some alleles becoming fixed, and that can have a result of lower diversity perhaps in a population, which might have some fitness consequences. But nonetheless, it is an important consideration because in smaller populations, they are certainly more susceptible to genetic drift. So small populations are more vulnerable to this random process. And so from a management or conservation perspective, it's really something that we should probably consider. So I hope at this point you have a good solid understanding of what genetic drift is, how it affects populations at a genetic level, and perhaps more importantly, how it might relate to some of your own work.